So let's talk about r squared. We'll start by the definition of the r squared. R squared is nothing but the variance in y hat divided by the variance in y itself. So what does it mean? So essentially, another way to say it, that's percentage of the variance explained by the model. So how much of variance is explained by the model. Okay. So if variance of y hat equals to the variance of y, it means that r squared going to be 1. So it's a perfect model. Or at least if you try to use r squared, you will claim that's a perfect model. And if the variance of y bar equals to 0, then it's a bad model. Because r squared is going to be also 0. Okay. But it's not always the case. So one thing, let's look at an example where the second so that's the first item. The second item, when the second item is violated. So let's say you don't have a linear data, but you have a data like this, right? Okay, and you try to feed a linear model. So the best linear model is going to be a constant model, just like this. Okay, so that's going to be a linear model. And the r squared of this model is going to be 0 just because the y hat is the constant. So the variance in y hats is going to be 0, so the r squared is 0. But it doesn't mean it's bad model. It's actually the best possible model. So it is a good model. It is a good model. Even though r squared for this model is 0. So r squared being 0 doesn't tell us anything, okay? And we can look also from different perspectives. So if we expand on this definition of the r squared, so it's again, so variance of y hat is just the variance in those points that belong to the line, beta 0, beta 1x. And the variance of y itself is just the variance of beta 0 plus beta 1x plus epsilon. So you remember the y's are just the values on the line plus the normally distributed errors along this line. And you remember that the variance of the sum is just sum of the variance if things are independent. So the variance of y bar is just the variance of beta 0, but beta 0 is constant, so it has variance of 0, plus the variance of beta 1 times x. And you remember that if we multiply a random variable by constant, then the variance goes up by constant squared. So the variance of y bar is just beta 1 squared times the variance of x. And the variance of y, in the same fashion, is going to be beta 1 squared times the variance of x plus the variance of this term, which is sigma squared. So in other words, r squared also can be written as beta 1 squared variance of x divided by the beta 1 squared variance of x plus sigma squared. Now, I can make this r squared to be as large as I want by making, so I can make this very large, okay? And if I keep this one fixed, and I just will increase the sigma squared, so sigma squared is how far y's lie along the line, then I can drive r squared to 0, so I can arbitrarily be close to 0. But again, it doesn't mean that the model is bad. I can drive sigma squared to be large by just simply rescaling values of y. right? If I put y in a different scale, then they might be further away from this line. But it doesn't say that it's a bad model, and it doesn't say that the linearity assumption is violated. So so the fact that r squared is close to zero doesn't tell whether bad assumption um, about the linear model, or whether this linear model is just a poor fit. Okay, in a similar fashion. Um, as long as beta 1 is not 0, so if beta 1 is not equal to 0, then I can keep this one fixed, and I can keep rescaling x, so the variance of x goes up. And then in this case, I basically going to have very large number here, and then very large number here plus some fixed number here. So r squared is going to be close to 1, so I can drive it as close to 1 as I want. But again, it doesn't mean that I have a good model. It's and it doesn't mean that linearity assumptions are not violated. So the value of r squared doesn't actually tell me that much. So that's why I'm going back to the statement that I said in the previous slide, saying that low values of s. So, and values of s is just the variance in y hat, which is just the sum across yi minus yi hat, and then squared. So, and 1 over n. So that's value is important. This value actually tells me how large my residuals are, and it tells me how good of a fit I have. Again, this value s doesn't tell me whether the linear model assumptions are violated or not violated. So assuming that linear model assumptions are not violated, I estimate my values beta 0 and beta 1 from the data, and then I calculate this value s, and this value s tells me how good of a model I have.